Hello, my name is Ignacio Ruiz, and in this video, we're going to talk about calibration of exotic pricing models using AI-based technologies and machine learning. In July 2024, Wilmot Magazine published this paper that you can see in the screen right now. In this paper, my friend Mariano Ceron and myself, we explained how we could use Chebyshev tensors for the calibration of exotic pricing models. In particular, we use as an example a rough Bergomi volatility model. Now, the motivation for this paper really came from these other publications that went out a few years before. It was these authors, they were using deep neural networks, DNNs, to do the same job. When we saw these publications, we really liked them. I do think that these are really good papers. And when we read this, we realized that this job could be done with Chebyshev tensors instead of DNNs. And not only that, but we thought that it could be done better with Chebyshev tensors. We didn't know at the time. We did the test, and that is what we report in this paper. So basically, this paper has the version that is Wilmot Magazine, this one here. And also for those of you that are interested in more detail, in our website or in the archive, we have a longer version where all the details are reported. So what I'm going to do in this video is basically answer these two questions. First of all, I'm going to answer how we can use AI and machine learning to ease the job of calibrating exotic pricing models. That's the first question. And the second question that I'm going to tackle is how do the different approaches compare, in particular, DNNs and Chebyshev tensors. As you can imagine, a lot of the details that I'm going to talk about in this video were also explained in this book. And in this book, they go into a lot of detail. So if you're interested in this level of detail, I suggest that you go to our book. The first thing that I'm going to do is to frame the problem well so we are all on the same page. First, let's talk about pricing functions. So a pricing functions can be seen as a function, a map between an n-dimensional space and the real line, where the real line contains the price. And this n-dimensional space contains three types of parameters. First, model parameters, something like correlation parameters, volatility, vol, etc. Secondly, we have market factors like spots, interest rates, today's market factors that affect the price of the derivative. And finally, the specific of the derivative, of the trade, of the traded derivative, like strike, maturity, these type of things. So all of this constitute the pricing function. And once we have a instance of model parameters, of market factors, and of trade-specific parameters, then the function provides a price. All right? So having said that, let's talk about implied volatility. Why? Because sometimes in the options market, when we have a price, we apply the inverse of the Black-Scholes function to obtain a volatility, and both of them are used indistinctively. This is a really important thing because for reasons that are beyond the scope of this video, sometimes it makes sense to refer to the price of an option as a volatility instead of price in dollars, for example. So this is done through this mapping. Once we get the price, we have the value of the spot, interest rate, strike, and time to maturity. We apply the inverse of the Black-Scholes functions, and we obtain a volatility. This creates a volatility equivalent to the price that we can put together with the pricing function itself so that we can get the composition of the pricing function P with the inverse of the Black-Scholes, and we get a function that goes from Rn, from the model, market, and trade-specific parameters, to the implied volatility. When we talk about a pricing function, we talk about P or this other composed function because both of them are equivalent. Okay. Now, once we have this in mind, it is market practice to build a volatility surfaces. But this means that we have strikes in one dimension, maturity in other dimensions. For example, I say for example because in terms of interest rates there are more dimensions. But anyway, let's stick right now to strike and maturity. And for each of these, given a price for an option in the market, we can obtain using, as I said before, the inverse of the Black-Scholes function, we can obtain a volatility. And by doing this, we obtain a function like a map, like a sheet that for every strike and maturity gives us a volatility that corresponds to the price of the option. All right. Now, calibrating an exotic pricing model means calibrating the parameters of that model to this volatility surface. How do we do this? Let's say that we have from the what I just explained before, we have a set of volatilities, market implied volatilities, and the model provides for a set of market factors, of model parameters, etc., provides a volatility as well. What we are trying to do is to minimize the distance between the volatility surface implied from the market, given by these V's, with the model implied volatility given by this function. So we get this equation where K goes through all the volatility points in the strike and time to maturity space, and we define this loss function. Calibrating the exotic model means finding the omega that actually minimizes this loss function. This is quite a heavy computational job many times, often because for example, let's say that we start here, okay, these two axes correspond to two values of the parameters space, and we're trying to find the set of parameters that minimize the loss function. So let's say that we start with a given value of those, with a random given value of those parameters. The loss function is here, and we want to navigate this loss function to find the minimum using the typical optimization routines. To do that, in each of the steps, we need to compute the whole volatility surface. Let's say that we have a 10 by 10 volatility surface, 10 strikes, 10 times the maturity, that is 100 points. In each of these steps, let's say that we do this 1, 2, 3, 400 times, for example, in order to get to the minimum. That means 400 times multiplied by 100, that is, in this case, 40,000 calls to the pricing model in order to obtain these values here. So 40,000 calls to the pricing model. If the pricing model per se is a Monte Carlo based simulation that is quite heavy to compute, the whole job of calibrating the model can be quite a heavy job by itself, to the point that it can be too slow, too expensive to do, so that it doesn't is in a commercial setting, it doesn't really make much sense. It doesn't provide any benefit. So what we are trying to do here in this video is to see how we can use AI functions in order to ease with this problem. Let's talk now about the solution using a machine learning method. The general approach is the following. There are two steps in the solution, one that sometimes it is called offline and another one that sometimes it is called online. The offline stage, in that stage, what we're going to do is we're going to calibrate a AI function to replicate the pricing function that we are going to use later in the calibration. So for that, we have to sample the space in particular of parameters, and to obtain a machine learning function that has good accuracy and replicates the original function. Once we have it, we go into the calibration per se. In that routine that I explained before, in which you're navigating to find the minimum of the loss function, in each step, instead of using the original function, the original pricing function, we're going to be using the AI-based function instead, which is supposed to be faster. So for this to work, three conditions need to apply that I've already suggested. First of all, accuracy. The machine learning function needs to be accurate enough. Ideally, if this is, for example, a Monte Carlo simulation, the same level of accuracy as the Monte Carlo simulation or something similar to that. Then, of course, for us to achieve this accuracy, it needs to be done with a limited amount of points, of sampling points. I'm saying this because for us to calibrate the AI function, we're going to have to sample the space, the domain in which the AI function lives. Sorry, in which the original function lives. We have to explore that domain. For us to do that, we need to do it efficiently because let's not forget that each point of that domain needs a valuation of the pricing function that is heavy to compute, and we want to do this as little as possible. So we need a method that is as efficient as possible as sampling the function, the original function, in order to obtain the desired accuracy. Once we have that, the third condition that we have is that the AI-based function needs to be very fast to evaluate. Why? Because we're going to call it lots of times in the optimization routine. And obviously, if the AI-based function is very slow, we're just swapping one problem of a slow to compute original function for another slow to compute function. We want the AI-based function to be very fast to compute. With this in mind, there are two clear candidates for the machine learning technique. One is deep neural networks, with all these papers reporting about it, and the other one is Chebyshev tensors, with these papers reporting about it. Let's talk now a little bit about each of these approximation frameworks. I'm not going to go into too much detail because I think it's beyond the scope of this presentation. But if you want more details, I suggest you can go to other videos that we have in the YouTube channel, or maybe to our papers or to our book. On one hand, we have a full Chebyshev tensor. What is a Chebyshev tensor? Well, first of all, what is a tensor? A tensor is nothing more than a grid of points in a d-dimensional space with values attached to each of them. When those points are Chebyshev points, then we have a Chebyshev tensor. What happens with Chebyshev tensors? Why are they so good at approximating functions? Because they have a special property, which is when the values attached to those points, to the tensor points, come from a function that has some basic properties that usually the most, if not all, the pricing functions have. When you have that framework, the polynomial in one or n dimensions associated with the tensor approximates exponentially fast the function that generated the value of those in the tensor points. What does that mean? What does this exponential convergence mean? That means that very few points, tensor points, are good enough to approximate the function with very high accuracy. So one of the key properties of the Chebyshev tensors is ultra-fast convergence. They are very good in approximation frameworks in finance because you have a function that is very heavy to compute and you want to sample it very few times. And because of that, because of the exponential convergence, very few sample points can guarantee that you have very high accuracy in the approximation. What is the challenge that Chebyshev tensors have? They have a course of dimensionality. Well, Chebyshev tensors are any type of tensor. Course of dimensionality because let's think about one dimension. And let's think for the sake of just a simple argument, we have 10 points per dimension. So we have 10 points in one dimension, 100 points in two dimensions, 3,000 points in three dimensions, 10,000 in four, etc. So the number of points grows exponentially with the number of dimensions. That means that as soon as you get to high dimensions, the number of points explodes so that you cannot really manage it. The framework is not manageable in a computer. So that is a challenge that they come with. On the flip side, we have DNNs. DNNs, you sample the space randomly, as somehow shown, illustrated here in this plot. In a Chebyshev tensor, you sample the space in a very prescribed manner so that you can unleash the exponential convergence. In a DNN, you explore the space randomly, and then you approximate the function with this type of framework. What is the positive of DNNs? The positive of DNNs is they are very flexible. Because of this framework, you don't have the constraint that you have with Chebyshev tensors, so they're very flexible to operate with and to work with. What is the challenge that they come with? That the exploration is done in a very, well, literally randomly. So there is very slow convergence properties of Chebyshev tensors, of DNNs. DNNs tend to converge to the function that you're trying to approximate very slowly. And what that means? That often you need a lot of points in order to achieve any decent level of accuracy. These are the two extremes. But then we have another type of tensor, which is a Chebyshev tensor in TT format, which is a hybrid of full Chebyshev tensors and DNNs. In a Chebyshev tensor in TT format, what we do is we explore the space randomly like a DNN, but the random points are Chebyshev points from a full Chebyshev tensor. So in a Chebyshev tensor in TT format, we are exploring the space randomly on the Chebyshev points. Because of that, we are inheriting some of the flexibility of the DNNs, but at the same time, we are also inheriting the exponential convergence, the ultra-fast convergence of the full Chebyshev tensors. How does this operate? We explore the domain in random points, in random Chebyshev points. Then we are going to express the Chebyshev tensor in a very specific way. It's called the TT format, the tensor train format. Then we're going to split the points that we have explored, that we have used to explore this space here, into training set, a testing set, like DNNs, again, inheriting properties from DNN. And then we are going to calibrate that Chebyshev tensor in TT format that we have started in a random manner to approximate as fast, as close as possible, the full Chebyshev tensor, which itself has exponential ultrafast convergence. And because of that, we are pushing the Chebyshev tensor in TT format to the ultrafast convergence of the full Chebyshev tensor. Now, I'm not going to go into more specifics, but I can show you an illustration of how the results that when you use these type of things. We have sampled a Black-Scholes option pricing function, 5 dimensions. So all the dimensions, which are, if I remember well, the spot, the strike, interest rate, time to maturity, and volatility, 5 dimensions. If we do with a DNN, we see this type of behavior. Here, the horizontal axis is the number of sample points, and the vertical axis is the error on the log scale. When we look at the DNN line, which is this line here, you can see that it starts getting better, but there is a point in which it doesn't matter how many more points you give to it, it hardly improves in accuracy. That is what I meant before by slow convergence. However, when you use Chebyshev tensors, these two versions here, one is the full Chebyshev tensor, and the green line is the Chebyshev tensor in TT format. You can see how they always keep on increasing. First of all, they are better than DNNs for this particular problem by 1 or even 2 orders of magnitude. And then as you increase the number of points, these things, the tensors keep on getting better all the time. You can see how this exponential convergence that I was talking about before is really being unleashed here. There is a prescribed way in which you can increase the accuracy of the tensor always. So, I mean, if you want to play with tensors, by the way, you can download our library, Mocax library. That Mocax library is something similar, like for example, TensorFlow for DNNs, in which you can use it to create DNNs easily. Well, our library, you can use it in a similar manner to create Chebyshev tensors easily, and then you can play with them really, and you can do I mean, you can do lots of things with them. And you can download it from Mortgage Intelligence. At the time of recording this video, it's free to download. And right now the plan is to keep it free for the foreseeable future. And also, just to let you know, at the moment, it's available in C++ and Python, and soon it will be available in Java. So by the time that you watch this video, possibly you already have the Java version available as well. Let's move now into the numerical results. One of the motivations of this piece of work, as I said before, was to see how could the same thing that was being done with DNNs, how it could be done with Chebyshev tensors, and to compare results. So for us to compare apples with apples, we try to replicate the piece of work, the research that was done for DNNs as closely as possible, this time with Chebyshev tensors. We are going to use a rough volatility Bergomi model in order to test all these methodologies. So let's talk about the Bergomi model for a second. A Bergomi model is a model in which that is defined by the following parameters. First of all, we have a vol of vol, then we have a correlation parameter, then we have a Hurst parameter, and then we have a volatility, a forward variance curve. So there are two versions of the model that we're going to work with. The first version is the one in which the forward variance curve is a number, is a scalar. So in this case, the input domain that we are exploring with the AI function has 6 dimensions. And for this, given that this number is not too high, we're going to use a full Chebyshev tensor. By the way, in the paper that is available in arXiv and in our website, we also have the version in which we use the Chebyshev tensors in TT format in this model. But to contain a little bit the length of the video, I'm not going to talk about that now. And also in the Wilmot paper, we didn't discuss it, again, to make it sharper and shorter. So we have model option 1, in which the input domain has 6 parameters. And then we have model option 2, in which it is the same as option 1, but this time the forward variance curve, instead of being one number, it is a term structure with 8 points. And so that in this case, the input domain that we are exploring with our AI function, it has 13 dimensions. Now we have to use a Chebyshev tensor in TT format. So these are the two options that we are going to explore. In the first one, when dimensions is 6, we are going to use a full mesh of 14,400 points. In the second option, in TT format, the dimension, as I said before, is 13. The full mesh has over 96 billion points, which is too much, obviously. So we're going to use a small proportion of them. We're going to use 20,000 points, as I explained before. They are represented by these red dots. And then from these 20,000 points, we are going to calibrate the TT format tensor to the full tensor. So that if you divide 20,000 by this number, you can see that this is around 10 to the minus 7 number of points. So this shows how the reduction of number of points using TT format is quite substantial. We have these two versions of the Chebyshev tensors. How do we measure accuracy? In order to measure the accuracy of the tensor of the AI function via Chebyshev tensor, we are going to do two things. We're going to generate a 1,000 volatility surfaces from different values of omega of model parameters. And then from these surfaces, we're going to do two things. First, we're going to do a brute force approach. We compute the volatility surface as such, and then we compute the volatility surface via the Chebyshev tensor replica, the AI function of the pricing function. And we're going to compare results. And what we're going to do is, from these 1,000 implied volatility surfaces that we have, we're going to compare the actual brute force volatility, let's call it that way, compared to the volatility obtained with the AI function. And for each of these, we have a statistics. We can obtain a read a root mean square error, and we can compare results. So what we obtain using the Chebyshev tensor in the case of dimension 6, which is model version 1, we obtain a maximum error of 0.6%, which is in line with the actual error of the Monte Carlo simulation that generates the data itself, the model itself. And also, once it is calibrated to this level of good precision, the Chebyshev tensor evaluation is around 10 to 100 times faster than the evaluation of the Bergomi model itself. So when we are using the Chebyshev tensor version of the model in the optimization routine, it is going to be much faster, 10 to 100 times, 10 to 100,000 times faster. This is for dimension 6 and for model 1. Let's go to the second model in which the dimension was 13. In this case, again, we have 1,000 root mean square errors. And then we see that the maximum error is 0.5%, and the Bergomi model calibration was, so the calibration through the Chebyshev tensor, the AI version of the model was around 40,000 times faster than the model itself. So again, good precision to the order of magnitude of the model itself, and much faster, so that the calibration exercise then can be done in a much more efficient way. Here, these two plots, you can see, well, this plot and the plot before, you can see the distribution of root mean square errors. And you can see how the error, for example, at 99 percentile, it is around 0.3% in this second model. And if we go back to the first model, is around, again, 0.3%. So and this accuracy, this 0.3%, is in line with the accuracy of the Monte Carlo simulation. So we have achieved good accuracy with this. Now, the question that we have is whether, so the second question that we have is, how does this compare to DNNs? We have established that Chebyshev tensors can be very nicely used in order to calibrate a volatility surface, because they have the same accuracy of the model itself, and they are much faster, between 10 and 100 times faster than the model itself. How do these results compare to the same framework, but using DNNs instead of Chebyshev tensors? And finally, let's compare then the results with Chebyshev tensors with DNNs. First of all, in terms of accuracy, we found an accuracy of approximately 0.6%. The reported accuracy in these papers that I told you about was around 1%. So maybe Chebyshev tensor is slightly better, but quite frankly, in line with DNNs, not much difference. It is in line with the error of the Monte Carlo simulation. So in that sense, both methods, I would say, are equivalently good. Now, the next thing that we want to explore was the building cost of the AI function, the effort that you have to do in order to calibrate the AI function. This is where the big difference comes in, because for us to calibrate to model 1, the Chebyshev tensor, we needed to explore the domain in 14,000 points. The same problem with DNNs, this was reported that they needed to use around 3.5 million points. So the difference is quite substantial. We're talking about a couple of orders of magnitude. For model 2, something similar happened. In model 2, we explored the function with 20,000 points. And with DNNs, they had to explore it with around 7 million points. So again, a couple of orders of magnitude, 99.7 and 99.6% more efficient Chebyshev tensors than DNNs. So when we get to the point of building the AI function, it looks like Chebyshev tensors are much more efficient than DNNs. And quite frankly, it doesn't surprise me. That was the thinking behind all this work that Mariano and myself did, because of the exponential convergence that Chebyshev tensors have. And that, as I said before, DNNs are slow to converge to the solution. So this is You can see now with your own eyes what that means in practice. And finally, once you have the AI function calibrated, in terms, what is the speed that we get? The speed of the, if we say that 1 unit is the speed of the Bergomi RAV volatility model, Chebyshev tensors were around 10 to 100 times to 100,000 times faster, while DNNs were around 10,000 times faster. What does that mean? This means that a typical calibration job in which we are looking for the optimal parameters, we're minimizing the loss function, would take in a kind of parallelized, not in a non-parallelized manner, so in a single thread, would take around 6.5 hours using the Bergomi, the brute force model, around 10 seconds using Chebyshev tensor, and around 50 seconds using DNN. Now, in this case, Chebyshev tensors are better, but quite frankly, 10 seconds to 50 seconds, it doesn't make much difference. I mean, it can make, depends on the context, but what I'm trying to say here is that in terms of speed, both Chebyshev tensors and DNNs are extremely fast to evaluate. So both are good enough. Let's put it that way, or very good. Both are very good. Let's put it that way. That's the way I would frame it. So in that sense, they are more or less similar. So let's summarize these results. On one hand, we have accuracy, obviously absolute accuracy using brute force. Well, there of the Monte Carlo simulation. For Chebyshev tensor around 0.6%, for DNNs around 1%. So in that sense, they're equivalent. AI calibration, Chebyshev tensors much better than DNNs, from 15 to 20,000 calls to several million calls, much better. And volatility surface calibration, both methods, Chebyshev tensors and DNN, improve substantially from brute force, and it looks like Chebyshev tensors are a little bit better. From all these numbers, the one that really stands out is the AI calibration. Why? Let's put this into context. A typical Monte Carlo simulation using the Bergomi RAV volatility model takes, in a C++ code, around 2.6 seconds. That was in our case. An optimized code took around 2.6 seconds. In the case of Chebyshev tensor, in which we are calling it 20,000 times, for 2.6 seconds called 20,000 times means we need 15 CPU hours. For the DNN, in which we needed 7 million points, this would take around 212 CPU days to compute. This is what I want to do now here, is to put in context what this 20,000 versus 7 million means. It means that if we want to do this job in 1 hour, and we parallelize it in a cloud, for example, in a cloud computing system, for the Chebyshev tensor we need 15 CPUs, while for the DNN we need around 5,000 CPUs. So as you can imagine, these numbers illustrate how the compute time or the compute cost of calibrating the AI function, it is substantially better with Chebyshev tensors than with DNNs by a couple of orders of magnitude. All right, so let's wrap up with some key takeaways. We had two questions that we started with. The first one was, how can we use AI and machine learning to ease the job of calibrating exotic pricing models? Well, I think we have shown how both DNNs and Chebyshev tensors can be used, and both of them, the model calibration gets accelerated by 10 to 100,000 times. So it is quite a substantial improvement. The second question that we had is, how do the different approaches compare? That is, how DNNs and Chebyshev tensors compare. I think the results were also very clear. The AI model calibration, Chebyshev tensors are substantially better than DNNs. And when it gets to the pricing model calibration, Chebyshev tensors seem to be a little bit better, but not far by much. The real difference comes in the calibration of the AI model, because think that we want to be, we want to calibrate this AI function with certain frequency. In fact, when there is a big swing in the market, we may want to calibrate it again quickly. And the last thing that we want is that when the market is in a turmoil and we want to calibrate things quickly, we have to do something that is either very expensive or very slow. In that sense, that is the fundamental reason why I think for this problem, for the reasons and for with the numbers that I have shown here, Chebyshev tensors do a better job than DNNs at the job that we have discussed here. This is it. If you want to contact us, if you go to our website, mocaxintelligence.com, we have a contact form. I'm more than happy to take any questions or any comments that you have. And finally, one little disclaimer. It contains a number of legalities that may be relevant to you. So if you are interested, please read it through. I'll leave it for a few seconds. Thank you very much.